So the first one is just what is probability and how do we find it? So this is just the definitions of everything. Um, the most important part is the formula here.
Occur.
So our formula in this
Event.
case for just regular probability
Number of ways the
is
event can
the
occur.
number of ways that an event can
Can
occur
occur.
divided by the total number of possible
Number of
outcomes.
possible outcomes.
So in our first example here, they're going to say how many ways can we select uh, a chocolate? Since there are 8 chocolate candies, we could select them 8 possible ways. And from the beginning here, they also tell us that there's 6 gummy candies, 8 chocolate, 7 hard candies. So there's 21 total. There's a number of 8 chocolate candies. So the probability that we would choose that is just 8 out of 21 or 0.3810. So there's about a 38% chance that you would select a chocolate candy. In most of these workshops, I'm going to be giving um, because I did create most of these workshops. I give the answers in 4 decimals because that's typically what we use for probability. But in this case, just read the question carefully and see what it asks. If it doesn't ask for anything, I would say 4 is a pretty good approximation. But sometimes they try to trip you up with 3 decimal places or 5 decimal places. So just be careful if they ask for those decimal places. But throughout this workshop, I'm going to keep it consistent with 4 decimal places. Our first example here, out of a bag of 100 tulips um, purchased from a nursery, it contains 45 red tulips, 20 yellow tulips, and 35 pink tulips. What is the probability that a randomly selected tulip bulb is pink? So we take the 35 up here, and that's
P
how many it would take, and then we're just going to divide them out because we typically say
Q
um,
equal
probability as a division. So this division is pretty
35
easy,
by
just
100.
0.35. And then the next one says, what is the probability that a randomly selected tulip bulb is yellow? So yellow tulip bulbs is 20. So we just come up here
20 out of 100.
and 20 comes on top. And since we still have 100 in the bag, it would be 20 out of 100 or
0.2.
0.20. Again,
Okay.
to make it 4 decimal places, you can always just add 2 zeros
Okay.
on both of these, and that will make it 4 decimal places. So when we're talking about probability, it's just the number of events occurring out of the total number of events. From a survey of 1,300 female adults 18 years or older, it was determined that 410 volunteered at least once in the past year. What is the probability that a randomly selected adult female volunteered at least once in the past year?
This would
So
be
we just take
410.
this 410
E
divided by the
equals
1,300,
10 divided by 100.
and we get
3, 3, 1, 5,
0.3154.
4.
And that's it.
Okay.
The next rule that we're going to consider is the addition and the complements rule. So the first rule is the addition. The key words for that is going to be or.
Or.
So we call this the disjoint, the randomly selecting event E or event F. So
E
this
or
or is connected to addition.
to addition.
Now let's say that we have something in common. So my first example is still that bag of candies, like selecting a chocolate candy or a gummy candy. But chocolate and gummy don't usually have anything in common. So if we have one that is has something in
Yeah, common.
common, what they have in common is just subtracted
Exactly.
at
At
the
the
end
end.
here.
Okay.
So this right here is what it would look like if we had them and they had something in common. So something like this would be if you're trying to choose playing cards and you say, well, I want a club or I want an ace.
Club or
Well,
ace.
both clubs has an ace. So you would say, okay, well, there's a 1 in 13 chance that I get a club that is also an ace. That's what we mean by mutually exclusive. Mutually exclusive means they have nothing in common.
Mutually exclusive, they have nothing in
So
common.
this is called the general rule because we don't know if anything has anything in common, right? So the addition rule and the general addition rule, the only difference between the two of them is do they have something in common? If they do not, then they are mutually exclusive. You just do the first one.
Okay, so the second formula that's in blue would
hmm
be like a gummy that has chocolate like on it. So it's like you're
Yeah.
subtracting the one that has like both.
So let's do something similar where we have like Reese's and a Kit Kat. And you're like, okay, well, what's the probability of choosing a chocolate candy or a Reese's? Well, Reese's are chocolate. So they have something in common, but not all of the candies that we have are Reese's. So what you would say in that case is if the gummy candy did have, like some of them did have chocolate on them, you would say, okay, well, the gummy candy out of the total number of candy plus the chocolate candy out of the total minus any gummy candy that has chocolate to it.
Oh, okay. Okay, that makes sense. Okay,
So
that's
mutually exclusive just means that they have nothing in common.
mutually exclusive. Okay, so if you
Mhm.
hear mutually exclusive, then you know you're going to be using the first formula.
Right, exactly.
Okay.
So mutually exclusive, they would not have anything in common. And that's why I say here P and E would be zero since they do not have anything in common. So they would be mutually exclusive. Now, the next formula that we're going to be talking about is the complement. And we use this quite a lot in statistics throughout statistics. So it's not something that you want to forget. We always use it because we're talking about 100%. Okay. So we
100%.
typically write that as 1
See,
because we're talking about decimals. We
1
rarely use percentage
is
unless
P
specifically asked for in statistics. So when we're talking
minus
about this, everything adds to 1. If I said, well, this happens 90% of the time, we can find how often it doesn't happen, right? So in the example of our bag of candies, uh, what is the probability of me selecting a candy that is
is
not
not
chocolate? Well, I already know what the
not
probability was
chocolate.
for selecting chocolate. We found it earlier
Only
in the
1 minus it.
paragraphs. So I just select that probability and I'm doing 1 minus because this is the probability that it will be chocolate. So if they all have to add to 1, if I just remove the probability that it's going to be chocolate, what's left over is
Okay.
going to be what's not chocolate. So this
Okay.
is what's not chocolate.
Okay, that actually makes sense.
So we use the complement throughout statistics. So even though we're introducing it in the early part of the probability, it's
1,
going to continue on throughout the
2,
rest of the semester. You're
3,
going to see it uh, continue. They're going to
4.
ask you, okay, what's the left-hand side or the right-hand side? And they are complements of each other, right? So we're always going to use this formula, and it may not always be written exactly like this, but it is a principle that we continue out because when we're looking at statistics, we're often looking at the bell curve. So the reason why we say that they are complements of each other
Mm.
is with that bell curve, what happens is it is symmetric about this. So this side is equal
Mm.
to our other side. They're equal to each other. They're exactly symmetric. So when we're talking about the complement, the whole reason we use it is because of that symmetry that we have with statistics. Everything has to add to 100%, which means if you subtract it to 1, you have what's left over after you remove it. So
So,
this
so,
is something.
so that bell curve. So this complement
Hmm.
method would be even true even if it was a bell curve that was skewed in either direction.
Mm. Skewing does happen, but it typically, so you learn about it a lot in the beginning, right?
Yeah.
You're not going to hear too much about it after that. And the reason is when we're looking at large examples, it's very hard to get a skew unless you did not do your experiment correctly. What I mean by that is if you have 1,000 participants, that's a pretty good sample size. If you did not set up your random variables correctly, then in that experiment, it can be skewed. But if you did set up your random variables correctly, it would not be skewed because it's so large. I think the minimum you have to have for a normal distribution, the bell curve, is 30. If you have a sample size that's greater than 30, it's going to look approximately like this.
Okay, so even for something that's like unfortunately like the American economy is probably a good
Hmm.
example of like something that's I believe that would be right skewed where it's like or no, that'd be left skewed because it's like all of like the billionaires have like all the money, and then like all of the like middle class have like less of the
Hmm.
money. So that would be like even that with if you took like the income, you could easily sample that using records of data that the government has. Even that would be like a normal distribution in all if you used all of the records of each individual income of each individual person in America.
Mm. I would say, what are your correlating factors? So in statistics, we're looking at correlation versus causation. Is this causing the other thing? So let's say you are looking at the amount of money that somebody has and you're looking at the neighborhood that they live in. So everybody in that neighborhood, let's take um their the amount of money that they make within a year and let's compare it to everybody else around them and we can say, okay, well everybody in this neighborhood makes over 50,000, but then you find a couple that don't, right? You will always have outliers, but outliers don't automatically mean that your data is skewed. You have to look at why are they outliers? Why are they not in my data set? If they're not in your data set because your correlation does not mean causation, because living in a certain neighborhood doesn't determine how much money you make.
Okay.
It can correlate. You can see a trend of, okay, well, most people in this neighborhood make around 50,000, so that must mean that everybody in this neighborhood makes at least 50,000. Well, no, because you can have people who have multiple incomes in one house, and maybe their combined total is 50,000, but only one of them makes 46 or 25,000. So you can there's other correlating factors that come to it. When we're looking at statistics, um, it is the mathematics applied to a data set. So much like physics is an application of mathematics, statistics is an application of mathematics. And in this application, you have to look at what is causing my experiment and how do those outliers affect my experiment. Because sometimes your outliers are due to other circumstances and they don't correlate to the causation of what you're looking at. So it's always, we are doing experiments here. Even
Okay.
though it's kind of silly in the examples that I choose, these are all experiments.
Okay.
So your experiment has to be set pretty well in order for them to work. Now, for example, with number 3 here, we have a bag of 100 tulips. I wouldn't say that's an amazing sample size. It's a pretty good sample size, though. Is
Okay.
that the entire population? No,
No.
but my sample size is going to reflect the population in a certain way because it is so large.
Okay.
So if you have a population that's greater than 30, that is a good approximation of the population. But
Okay.
your sample size is never going to fully reflect the population. That's why it's all about chance and probability, and it's not about exact.
Okay.
Because if I reach my hand in the bag, there is a possibility that I just pull out 5 in a row, 5 red tulips right in a row. Is that a very high possibility? No, because there's 45 of them versus the total 100. So looking at that, all of it, um, the probability, the chance of me getting 5 of them just off the rip every single time is not going to be very high.
Okay.
But there is the chance. We can't say it's 0 because you can do it. But randomly, it's going to be hard.
Okay.
So that's why when we're looking at this bell curve, although askew graphs do occur, they mostly occur when your sample is either not a reflection of your population or your experiment has failed in some way.
Mm,
Either your sample size is not big enough, your sample size does not reflect your population, or you did not create your random variables very well.
okay. All right, that makes sense actually.
Yeah. So we always have to look at the context with these ones.
Okay. Especially with statistical analysis.
Yes.
Mm.
And if you do anything later on with mathematics, you will see that. I know from my degree with pure mathematics, we did a lot of statistical analysis when it came to mathematical models, which means taking a look at a real world example and how does this change? Because rates are never consistent. So you have to look at how much is this changing over time. Um, And it's really important for you to look at the context of anything when you are doing statistics, because context provides a lot of clues. It's all about word problems for statistics.
Mhm.
Yes, we do a lot of mathematics behind it, but especially in this course, because it's elementary statistics, the mathematics has been done for you.
Mhm.
You get formulas. You don't have to find the area underneath that graph. It's been done for you. So when you are looking at this in statistics, it's all about the context of what you are looking at. So, for example, with number 3, since I have a bag of 100 tulips and then each one of these colors, right?
Mhm.
If we're looking at this in context, I can see that the number of red tulips in comparison to the number of yellow tulips is fairly large. So the probability of getting a red versus the probability of getting a yellow is going to be higher just because there's more of them. That's the context that I'm talking about.
Okay.
So the first question is asking if you are randomly selecting a pink or yellow, what would be the probability? So we start with pink and we're
Pink.
doing the 35 pink tulips out of 100. And then we
Yeah,
also
for
have
the red.
20 out of 100.
20 out of 100. Yeah.
Now, when we are doing this,
Pink.
there's one thing that will pop up later that we're talking about, and that is with replacement. If they do not say
With replace.
that they are not replacing it, so they'll say without replacement. That is a very important phrase.
Okay.
That means they take the bulb out and they just put it off to the side. It does not go back in the bag.
Right.
Nowhere in this example is that said. So we are assuming they choose a pink tulip, put it back in the bag, shake it up, and then they put their hand back in the bag and they select a yellow tulip. That's what we're assuming. If they do not say without replacement, it's always being replaced back in. Your total
Okay.
does not change.
Okay.
And then we just add them together. So this would be 55 out of 100, or, and again, we just divide it out. Typically, like I said, I'm going to keep it as 4 decimal places. So I'm just going to add on some zeros.
Fine.
Now, B is the complement. This is what's really important.
Where's the probability of
So
not selecting a
the
yellow
complement,
tulip?
since the probability here, they want us to find the probability of not. That's our keyword, not selecting it. Um,
Mhm.
we're
Not
going to
selecting
do
yellow tulip.
1 and then minus the
Mm.
probability of selecting a yellow one.
1 minus 20 over 100.
So 1 minus the probability of
1
selecting
minus
a yellow one was 1 out
1
of 100, or 20 out of 100,
100.
which means there would be 80
80.
out of 100 left over, or
100.
0.8 0, 0,
0.8.
0. Again, the reason why this is so
100,
important with the complement is because I may not know what the not is, but I do know what yellow is. So I can use yellow to find out what it wouldn't be. And I can see that the ratio of yellow to the ratio of everything else is going to be very, very low. So it's a very big chance, 80%, that they would choose yellow, that they would not choose a yellow. They would either choose red or pink.
or pink. Okay. Okay.
Any questions on the addition formula?
No, no questions. That part makes a lot of sense, actually.
Yeah. It's with this one they are also mutually exclusive. You can't have a red bulb that's also a pink bulb. Um, in this specific example. However, in real life, we know crossbreeding exists, and you may have a bulb that has both colors to it just because of crossbreeding. But in this specific example, there's not.
Okay.
Find the probability of excluding leap years from calculations. Um, so we're not counting the years where February only has 28 days
The probability that a random selected individual
or
who was born the
29
first of
days.
the month or was born in
So
April.
we're just looking at it as February has 28 days and the rest of the months are all the same. Compute the probability that a randomly selected individual has the birthday on the first of a month or is born in April. So the first of a month,
First
there's
of all,
12
there's
possibilities,
12
right?
possibilities. Yeah.
Out of how many days of the year?
12 out of
365,
365.
approximately. Statistics is not a perfect science, right? So we're using approximate numbers here. 365 is not the total days in every single year. They do change, but
Yeah.
365 is a good approximation for it. Or was
Minus
born in
or
April. Well,
was
how
born.
many days in the month does April have?
Uh,
It would
30.
be 30.
30.
So here we're looking at 30 days out of 365.
365.
So we just add those together and we get 42 out of 365, and then we divide.
42 out of 365.
So you can see it's not that low of a
Equal
possibility. And
point
that's because
one
these are both
five.
very high in comparison. If we had said the second week of a month, or if we had said one specific day, that's going to be a very small approximation because that's one day out of a total of 365. So having a 12% chance, which is what this is, that's a pretty good chance in comparison to the context of what we're looking at.
So the reason that the prob so when you say either have blank or blank, the
Hmm.
probability is actually going to go up. You're going to add something to the original probability because
Yeah.
you are now expanding how many options that there could possibly be out of the total. So that's why
Yes.
you always add when it says
Yes.
or.
So this, yep, you add because the keyword or it means disjointed. So they're not like together. With an and, that means intersection, where they are colliding together. But an or means just both of them. What happens if we have both at the same time? This happens or this happens. And when we're talking about statistics and in mathematics in general, we're talking about the inclusive or, this or that or both.
Uh-huh.
So when we say or, we're not saying this happens or this happens. We're saying both happens. What happens if both? Now that does get confusing because the and also uses the word both, but in a different context. So we're using the disjointed inclusive always in math. Unless they specifically say otherwise, it's always the inclusive or. So when we're talking about the or, since we're talking about two different things together at the same time, it will add together. They will be just this happens and this happens separately. Two separate events that are just carried together. Whereas with the and, it's more like an intersection where both of them are colliding to each other. This happens and it affects this happening. So they would be multiplied
Okay.
because the probability of an and getting them together, intersecting with each other, is going to be a lot harder.
Okay. And so if you
But
used
mhm.
and, the probability would go down
Yes,
because you're
yes, because
multiplying
you're
a
multiplying.
fraction. A
Hmm.
fraction by definition has a denominator that's, well, not by definition, but like typically is the
You got it.
denominator is larger than the numerator. So when you multiply
Yes.
it by some number, that division in the bottom that you're dividing by
Hmm.
is gonna become larger, which means your net is bigger for the impossibility.
Yeah, you got it. That's exactly what it is. For the
Okay.
and, the probability will decrease, but for the
Okay.
or, the probability will increase.
Yeah, because and is like saying like,
Hmm.
what if you were born on like, well, no, born would not make sense for that, but like, what if you were saying like, what is the probability that you meet two people and both are born on the first day of 2004? That would be
Yes,
like a very 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 small
very
possibility.
large. Yes, exactly. And that's because both of them, they're intersecting with each other. They
Okay.
are combining with each other.
Yeah.
Whereas with the or, okay, what if you have somebody who is born on the 12th of February, or, they could have been born on a different month? Or you meet somebody who was born in April. Like there's a lot of possibilities in that, and you don't know for certain
You're including more
because the or,
possibilities.
exactly, you're including all of the possibilities. This or that or both. You're including all three of those. This or that or both. That's always what we mean.
Okay.
Whereas an and is a strictly both.
Yeah. And
Hmm.
makes sense if you think of it in the context of like, maybe you're like playing a game or something and you're trying to like figure out like what would be the most advantageous for you. Like
Hmm.
if you're like, oh well, you would have let's make a deal that if this lands on this or this and this at the same time, then I'll give you XYZ. It's like you're gonna say
Right.
this and this because you know that if you do this thing and this thing at the same time, the probability is gonna be lower. Opposed to if you're the person that wants to receive whatever it is, if you
Hmm.
win the gamble, you're gonna say okay, either this or this, because then you know subconsciously that the chances of it being this one or the other one is higher. Does that make
Exactly.
sense?
That's a yes, that is a very good way of looking at it. Hmm. That's why a lot of the times they use, especially in these sections, they'll use card games to explain both the and the or.
Because you're gonna
Because an and, if I'm saying what's the probability that I choose a card that is a spade and it is a four? Well, now you're choosing the four of spades. That's a smaller possibility than if you say, well, I could get a four or a spade. Well, that now you have fours, which there's four fours, and there's 13 spades. So you could get this or that, and then you just subtract away what they have in common, which is the four of spades.
okay.
Yep.
Hmm.
For this one, they want a randomly selected individual that was not born in November. So we do one minus, and then November, I believe, is it 31 days? Let's look at it. 30 days. So 30 days out of
Be the
365.
randomly selected individual is not born
So
in.
then what's left over is
3
335 out of
equal 1
365. So
minus
you can see that's going to be a really big possibility.
35 equals 335.
0.6. So the larger it's going to be. Now, by the way, because we're going to get to the independence and the multiplication rule next. Um, this also works for multiplication. The complement works for literally any probability. If you want the opposite of it, If you want to see what happens when you don't choose that probability or don't choose the month of November, this complement will work for literally any type of probability. It's not just for the addition rule. Even though it has subtraction, it works for everything.
So if you wanted to do like the opposite, it would be what's left of 1 minus 0.9306.
Yeah,
Okay, so I
yeah.
don't first. I also wanted to ask, like, I'm doing 335 divided by 365 on my calculator, and I'm getting 0.917.
Oh, that's
Eh,
because I did 360, not 365. Good
Oh,
catch.
okay.
9, 8. And then any more questions about the addition rule?
So you did say like if you wanted to do the opposite, like find what is the
Hmm.
chance that someone was born in November, you would just do 1
Hmm.
minus 0.9178.
Yeah.
Okay.
And you can check it pretty easily because 30 divided by 365 should be 0.822. And
Uh,
if I subtract these, they're the same.
okay.
Rounded, they are the same. When you do that calculation just on the calculator, you have to round it first. So just know that it's a rounding error. Um, with statistics, like I said, it's not a perfect mathematics. There is always, always, always going to be a rounding error. That's why on my math lab, if you ever look at like you hover over the answer box, it will tell you, oh, this answer is within 2%. This answer is within 1%. So that means there's a 1% error on it. So you could be within 0.01 of the answer and still get it correctly
Okay.
because there's always going to be a rounding error, no matter what. Our charts that we use for statistics, especially later on in the next couple of chapters, they're also going to have rounding errors. So they know that there's going to be some sort of, I rounded differently than you rounded. So if you're off by just a little bit, it's okay.
Okay.
So when I calculated it, it was actually like 0.08219, but when that's rounded, it's rounded to the same.
Okay.
So the next part, independence events mean that they do not affect the probability of each other. So if E and F are independent, they do not affect the probability. So this is where the definition for mutually exclusive for the and
Mutually
comes
exclusive
in
for the and.
because it deals with independence. So before I said mutually exclusive is if they have anything in common. For the and, it's more of do they affect each other? Does the first event have any consequence on the second event occurring?
Okay.
So for example, if they are independent events, um, what's a good one? If you take out one of those tulips and now you're trying to calculate the next one, well, that's going to change because you're now taking out
Okay.
one from the total.
Right.
So it's going to have an effect on the next bulb that you're choosing because you removed it.
That'd be like
So
the
that's what we mean.
replacement. That'd be
Yeah,
with
without
replacement.
replacement.
Oh,
Hmm.
that'd be with. No, that yeah, that would be without replacement because you're not putting it back in.
Exactly. So without replacement is going to change how the probability is on the next event
Wouldn't
because you're
it?
not putting that back in.
Wouldn't it just minus? You just take one away from the denominator.
Yes, but let's say, so I had 45, 20, and I had 35. If I removed and I took one out and I had 100 out of 45, well, then the next one that I'm doing, right? That
Mm-hmm.
45 is gone. Let's say I choose another red bulb, it's now 44.
Oh, so
And
you.
it's not out of 100, it's out of 99. So it's
Oh,
changing
okay.
the probability. That's what we mean. If it does not affect the probability, that means it's independent. If they are dependent, the probability of E is affecting the probability of F.
What would be an example of one where taking one out of a group would somehow not affect the probability?
Mm,
Maybe like winning the
if
lottery?
if you're if you're doing if you're removing it without replacement, you're always going to affect the probability.
What if it's something that's infinitely generated though?
But you're looking at sample sizes.
Oh, okay.
So if you're changing your sample automatically, you're changing the outcome. So
Okay.
you can't, in statistics, we use set examples. You can't have, the other reason is, I'm just going to scroll up to the top here real quick. This word that we use here, discrete. Very rarely do you ever get a probability that is not discrete. And the reason is we're looking at set sample sizes. And the sample size for the flowers, it was 100. If I change that, that changes everything. I can't have an infinite amount of tulip bulbs because there's not an infinite amount in the world. There's this discrete number. There's a countable number of bulbs. Can they be generated? Sure, slowly over time, but not infinitely.
Okay.
Every day in the world, there is a set number. So discrete means there is an end,
So
a start and an end.
realistically, we're using discrete.
Yes.
Okay.
And throughout this one, it is going to be discrete. Um,
So we would never use continuous in real life?
Continuous probability does exist. It is a little bit more complicated, because you wouldn't be able, it's not like this where we're looking at it in a vacuum.
Okay.
When we're doing a sample size, especially in the next ones, um, continuous probability refers to something that ultimately can be continuous, like a function, or
Like a
I
measurement?
wouldn't say like a population, but something like a graph or
Like,
energy would be a good example of something that is continuous. It can never be created or destroyed. But we
okay.
don't do a whole lot of statistical analysis
Okay.
on energy systems.
Alright, fair enough.
We do, but just not a whole lot of it, and it requires a different background in mathematics
Okay.
because you would be using differential equations to do that.
Yeah. That's far down the road.
Yeah.
Hmm.
Um, so the proofs for this actually occur in calculus 2. That's where we get area underneath a curve and stuff like that. So all of the formulas that you learn in statistics, you learn how to get them, or you learn the mathematics behind them in calculus 2. So this is far before anything that you would really require for it.
Okay.
Um, but yeah, differential equations is where you would more learn about continuous functions.
Okay.
Um, so discrete is typically what we're going to look for in here. We're always looking at a set of numbers.
Okay. That sounds
So,
more reasonable.
yeah. Um, so for independent events, we're just going to use the probability of E times the probability of F. Whereas if they are, and you can have them, this one is the same formula, but more than two events. So you can have more than two. And you'll see that sometimes, because the countable ones, you'll see like 2 raised to the third power. This is a probability. It's just 3 events, all having the same probability. Um, Now, with 2 independent events or more, you're just going to multiply them.
Okay.
If they have something in common, you have to divide it. So with mutually exclusive in terms
They something in
of,
common you have to
or
divide it.
dependent is what they call them, in terms of the and
Hmm.
formulas, you actually divide them out instead of subtracting it. Because you're multiplying, you do the opposite. You divide.
Oh, that actually makes sense. So because like Because you want to like okay, so you wouldn't subtract because you subtract when you're doing addition because subtracting is the opposite of addition, but when you're
Yeah.
multiplying you do division because the opposite of multiplication. That makes sense. Okay.
Yeah. So they also call it by a different name. Those are the given formulas. So they'll say F given E, and they will actually say the word given in there. There's no other word for it. I know in mathematics sometimes they kind of get a little weird, but for this formula, if they're talking about the dependent events, they say given. Event F is happening, and we already know that event E has happened because event F is happening. That's what they mean by given. So the way they write it is F and then a bar E. And the formula is, I believe, the and divided by event E. Let me look at that real quick because I always mess them up. Um, Given statistics formula. There we go. Oh, yeah. Um, yes. Yeah. And um E and F, it doesn't matter the order on this and. They'll be the same. And it's divided by event E. Yep. So when we're looking at this, this is the formula, but just to keep it consistent, E and F. But with this formula, this is the one that they have something in common. So this is the not mutually exclusive or dependent. So F depends on E happening. That's what we mean by given. Just
And
wanted to point that out because you will use it.
okay. And so what this is basically saying is we're doing the probability of F times the probability of E divided by E. Probability of
Yeah,
E. So
yeah.
what that means is that we're taking the probability of F happening and dividing it by the probability of E, but then we're minusing it by the probability of E happening E amount of times.
Yeah. So you're looking at it in context of E. So instead of the total, you're doing E. Because if you look at this, this would be event F over the total times event E over the total divided by event E over the total.
Yeah.
The totals will all cancel out. And this is actually the
So,
numerator is what they have in common.
but realistically, you don't even have to like because probability of F happening over T. Well, the way that you read it before is just F divided by T times divided by one.
Pretty much. You will be left with
Because
what's going to happen is the totals actually cancel out. It's kind of hard to explain without a specific example of it, but the totals will cancel out, and this is what they have in common. Instead of it being the multiplication of them, this is what they have in common.
okay, so this is just a way of like communicating what they have in common.
Hmm.
But realistically, like when I see this and I'm thinking about what I know about probability and what I know about algebra, I'm
Hmm.
seeing the probability of F and that's it. Because I know that the probability of E over the probability of E is just equal to 1.
So let me see if I can get a good example of it.
Because if those are
Because when we say in this in this formula, when we're saying and in here, it means what they have in common,
okay, so first so
the
you wouldn't
intersection.
okay. So here it's like an algebra when the division actually acts as like a parentheses. So we're
Yeah.
multiplying those first on the in the numerator and then we're dividing it.
Hmm.
So it's not as like clear cut as it would be in algebra where well actually no, because in algebra you'd have to
It's
multiply the two numbers at top first.
it's better if you look at it on a chart, because typically when you're given the given formula, they give you F and E. they give this to you. If they don't, they give you E and they give you F.
Okay.
So they either give you, they have to give you one of the three, right? Automatically, but they have to give you at least two of them. So typically they give you this and this, or they give you this and this.
Okay.
So
And
they
then,
have to give you two of the three so you can solve it.
well, then from there it'd be pretty simple. You would just multiply f and e,
Yeah.
and then you have your answer, and then divide.
hmm
Obviously, like divide it. Okay.
it's honestly, it's not hard. It's just my problem with this formula is always flipping it around. I
Okay.
always flip which ones it is. So I would just remember if whatever letter is here, whatever probability you're finding here goes on bottom. The total of this goes on bottom. And that is what they have in common.
Okay.
But you will use the given formula in this class. Conditional probability and multiplication. So here it is, right here. There you go. Don't know why I wrote it up here. Apparently, I already wrote it. So yeah, this is the conditional. If they are dependent on each other, this is the probability that we are using. And I wrote it in the exact same way, apparently. But yeah, so this is what I'm saying. With the example, they have to give you two of them. So they give me these two, and they're like, all right, what's the other one? Well, so I just plug it into the formula. Well, P of F given E
Yeah.
has to be 0.22 divided by 0.35, which is what I did over here to get
Oh.
that 0.6286.
Okay. So. Hmm. Okay. So it's more about just plugging in the values opposed to
hmm
actually doing the arithmetic. It's really
Yeah. They
okay.
will either give you the values like this, or they will give it to you in like a chart where they break down the totals of each and then the intersection of each. So let
Okay.
me see if I can find a good one.
So here you're what this basically means,
hmm
this fraction is, this is the probability of f and e occurring at the same time, and then dividing that by the probability of getting e.
Yeah. Yeah, that's a good way of looking at it.
Okay.
So here, let me see if I can copy this and make it a little bit larger, and then I'll just delete it after. Um, this is a good way of looking at the chart. So let's say, um, well, nah, we won't do that one. We'll do a different one that has like the totals and of each thing. No. There we go. That's what I want. Okay. So what we mean by given, we would say, all right, find the probability that each one of these hospitals, right? So we have the target population, the respondents, and the percentage, and then they give us the totals of everything, right? The percentage makes sense because it has to add to 100%. Well, what they would say is a column intersecting with one of these. So let's just say we have the European Gaza hospital, and we want the number of respondents. So you would say, given that we have the European Gaza hospital, what find the probability of the number of respondents. So this right here would be your and, because that's where they intersect. Right there. And then you would just take this total, because this is the total of E, right? And this is E and F right here, because that's where they intersect with each other. And that's what I mean by either they give you the values or they give you the chart and ask you to find it. from the chart, it can be a little bit tricky because there's a lot of numbers on there, but just so long as you're being consistent, you can find it from the chart. So either they give you this or they give you the chart. I don't think I have yeah, I do, right here. So we'll do both. Okay. Now, here's the example. Again, using the same bulb example. I was not creative in this when I was making it because I was just like, let's keep it consistent. We're using the same exact example 50 times. So in this bag of 100 tulips, what is the probability that they are both pink? And this happens without replacement. So this is where our first one would be 35 pink bulbs out of the total 100. Then the second one is going to be 34 out of 99. And then we do 35 times 34 divided by 99 times 100. And we get 0.1202. Now these are not independent events because the first one is changing the second one. When you remove that bulb, you're now changing the probability for the next one.
So this is dependent.
Yep.
Okay.
With this one, the first one is yellow, or I'm sorry, the first one is red, so 45, and the second one is yellow, and that's going to be 20. These ones are not changing, but we start with 100 and then we come down to 99.
Okay, so this is like so this one we have to know the specific order in which we're taking them out to actually do this.
Right.
Because if we take out one of the red, we need to use 45 out of 100 because we haven't taken any out yet. But then
order is important. Yes.
When we go to take out the yellow one, there's still going to be 20 yellow bulbs because we know that the one we took out was red. But we know that that one red is one of the 100, which makes it 99 in the denominator.
Exactly. Order is important in this one, and we'll see that with Part D as well, because they don't specify in Part D. Part C says, what is the probability that the first one is yellow and the second one is red? So this one is different. We start with the yellow, and then we go to the red. And you'll notice something funny happens. Doesn't change. Because you still get, it's the same fraction. You're still multiplying them. So you still get 20 times 45 over 100 times 99. That hasn't changed.
So this is happening because the probabilities are still the same.
Correct.
They're kind of like equaling each other out, essentially.
Essentially, that's a good way of looking at it. So in these two examples, order doesn't matter because we are multiplying. If we were to do addition, order would matter, right? Because 45 over 100 plus 20 over 99 is not the same if you do it backwards. Well, actually, no. It would be the same because you're still adding similar fractions. But addition is associative in the same way that multiplication is associative. However, the difference between multiplication and additions when we're looking at it is if I flip those numerators around in addition, it's not going to be the same thing. Because now you're changing the quantity, you're changing the ratio. But in these two fractions, although I have changed the ratio, they are still multiplied. A multiplication is associative. So just because the numerators flip, the denominators haven't really changed. And since we're still multiplying the numerators and the denominators together, you're not going to see any change there. But what happens if we don't specify? This one says, what is the probability that one of them is red and the other one is yellow? Well, if one of them is red, we are going to have either this first one being red or this second one being red. And then you can either have this one being yellow or the first one you pick being yellow. So there's two possibilities. The first possibility is right here. So there's, because they don't specify the order, there's two different ways that it can occur. Either we choose the red first and the yellow second, or we choose the yellow first and the red second. That's where this is coming from.
So this, on either side, the left side and the right side of that plus sign, is the same probability.
Yes.
So then what you can really do is just add 0.0909 to the same number.
Yes. And you get 0.1818.
Okay.
So yeah, the whole reason there's an addition in here is because you're saying this. Either we choose red first, yellow second, and then there's that giant, or we choose yellow first. First,
yellow second, or yellow first.
Red second. So that or is going to have the addition. So there's two types of probability we're doing here.
Yeah.
The dependent multiplication and the mutually exclusive addition.
Mutually exclusive as in?
Neither of these events relate to each other. Whether you're choosing a red first and a yellow second, or a yellow first and a red second, they don't relate to each other.
Okay.
They don't have anything in common with those two events.
Okay. So the likelihood of getting red first and yellow second is the same likelihood as getting yellow first and red second.
Yeah, same probability.
But wouldn't the probability be higher to get red first because there's more reds than there is yellow, so you're more likely to get a red first than a yellow first?
But we're multiplying them. So even though we still have, we do have, it would if we were doing red or yellow. If we were saying this or that or both. But we're not saying that. We're saying we're choosing red, we're choosing yellow.
But in this one,
and we're not replacing them. So we're doing that concurrently. We're choosing it, we're choosing it. We're not looking for this or that or both. We're doing just both of them. So that means with the multiplication, it does not change the probability. Because with the 45 over 100 times the 20 over 99 versus the 20 over 100 and the 45 over 99, you're still having the same multiplication. 20 times 45 and 100 times 99. They're the same thing. And that's what we proved up here. They're the exact same thing. We still have the 100 times the 99 and the 20 times 45. No matter which order it's in, you still have that same probability.
Okay. I understand like the math behind it and like the rules, but like intuitively my brain is telling me that if there's more red, then when you go to pick out one of the tulips, you're probably going to get a red. And you're going to get that one first because the likelihood of you getting it in the first place is already higher than getting a yellow.
Sure. 45 over 100 is definitely more than 20 out of 100. I agree with that.
Yeah.
0.45 is definitely bigger than 0.2. However, we're not choosing them one at a time. We're taking them both.
Oh, we're taking them
Both are
both at a
getting
time.
removed.
Okay.
We're not doing event A, putting it back, event B. We
Okay.
are doing event A, event B.
Okay, so then that is like if you grabbed two with one hand. Okay. So would you
Yes.
say that that's like a very actually important detail? Because if I mean this kind of like idea kind of it doesn't really make sense if you're doing one and then the other. You know, because if it's like first then second, because if you're saying well red first and then yellow second, well then there's no point in putting one first and one second if we're pulling them both at the same time.
Well, that's what we just showed.
Oh, okay.
That's what I'm saying. In both B and C, that's exactly what we're proving is that there is no point in saying that red is first and yellow is second,
Oh,
or that
okay.
yellow is first and red is second. They're the same probability. That's what we've just proven.
Okay.
Now, if we said we want either of them, that is a completely different probability altogether because we're not stating the order.
Okay.
There's more than one possibility. So that's why I say for part D, you have to do the or probability inside um, that multiplication. So you have to do the multiplication and then the addition as well because you're not specifying. Although these two probabilities are the same, they're specified. If we don't specify order, then there's more than one possible way that I can choose them. So let's say there was three ways because they wanted to choose three. Then I would have to do all three possibilities. Does that make sense?
Yeah, that actually makes sense.
Um, I know we're out of time for the workshop, but I just wanted to show you real quick the given, because I did put a chart in here for it. So the first one says, find the probability that an individual is male and has done 1 to 2 activities. So we go to male,
Mm,
right?
one,
And one
two,
to two activities. That would be 85
85
out of the 143.
out of the 143. Okay, so it wouldn't be out of the entire total. It'd just be out of the total that already did 85.
Now
Or that
you
already did
could
one and
do out
two.
of the whole total. And this is where I was saying it gets a little messy because they do cancel each other out. So the 85 out of the 143 is the total. Because you're saying a male given that he has done 1 to 2 activities because they have something in common. They're not mutually exclusive. They are not dependent or independent. You could say this is the and right here out of the total number of 1 to 2 activities out of the total. So they will cancel out. That's the thing, is they do eventually cancel out to just get you this. Or I guess you could say 85 out of 400 over 143 out of 400. The 400s cancel out. And you're left with 85 out of 143. So you could do the totals, the absolute total of everything. It cancels out.
Yeah, because this is like saying 85 divided by 100 divided by 400 over
Mm-hmm.
143.
Mm-hmm. 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 Yeah. So that's why it just cancels out to this one. Because you're doing the individual males out of the total, so 85 out of 400, and then he has done 1 to 2 activities. Okay, there's 143 out of 400. What is the probability that a randomly selected individual has done 3 to 4 activities given that they are female? And
That range significant in 3 to 4 activities.
so given here, again, you're going to look
Given
at
3 to
the
4.
first one, 3 to 4 activities,
56 over
given that they
103.
are female. So this one has 3 to 4 activities first. So when I
56.
was looking at that formula, let me scroll back up to it here. When we're looking at this formula, you see how it says F given E, and then E is on bottom. So it's always the second one. Given that they are female. Given that they are
One
female
female.
means female has to be on the bottom.
Oh,
So I look at the total number of females, 200,
mm.
and the 3 to 4 activities, and I do that.
It wouldn't be a 103 on the bottom?
Nope. Because you're saying this is event F and this is event E. So if I do the probability of F
Uh,
given E, it's going to be
56.
their intersection. So we usually write that with the little n. Their intersection over E. Well, what's the total of E? It's 200. It's not the 103.
Oh, because E is the how
Because
many females there
3 to
are.
4 activities given that they're female. Female is inquired. You have to have that because it's given that they are female.
Okay, yeah, given that they're female. Okay, so then you wouldn't
So we
even
would
think
say
about
3
the
to 4
males.
activities is what I want, but they're female. So the total number of females is what I need.
Okay. So then you would use 200.
So that they will always say for this formula, they will always say given. They're not
Okay.
going to give you like a that. But that's two ways that you can do the given formulas. The first one was an and. So that's not the answer that's at the bottom, but just so you know, that's how you do the given formulas. Given has to be F is the first one, E is always the second one because you're saying um, E is sufficient and proof of F.
Okay, so
E has to happen in order for F to happen.
there E is it's always given E.
Yes,
Given E.
always given E.
Okay. Alright. Could I see the formula one more time? For the
Yeah.
P of F E. I think you passed it,
There
so
it
then.
is. Yeah.
Okay, so you multiply the two because it has an and between, and then okay.
Yeah, they should always give you, if they don't give you the and, they have to give you the other two. So again, it's a little confusing because they say and here, but they mean intersection. They mean what they have in common, not necessarily multiplying them. You can find it that way. So let's say I were doing this formula and I wanted to do the and. If I didn't have this 56, I could take the total number of activities, 103, out of the total 400, right?
Mhm.
Multiply that to the total number out of the 400, but then we still have given E. So this is
Five given
out
E.
of a total number. And I think that would be the 103 plus the 200. But when you start to break down this formula, it's actually all going to cancel out. So the reason why I don't like saying that it's the intersection and not the and, because it's what they have in common. Intersection means what they have in common. Whereas and in this context doesn't mean what they have in common. So they're using two different ands.
Okay.
So that's why I put the intersection and not and here. But yeah, it's a little bit harder to use the and formula to find it, but you technically you can.
Okay. Opposed to just using intuition and just writing the formula or writing the probability.
Right.
Okay.
hmm Yeah, so I think with this one, if you're doing it out by hand, you actually have to divide by what they have in common. Um, or something similar like that if you were doing the and then, but you have to divide by what they have in common. You have to take away what they have in common in order to have that formula. Um, and that's what the given formula is really saying, is that they have something in common, and that's what happens.
Okay.
We are out of time for the workshop. The next portion is the counting techniques, which is the permutations and combinations. They're very, very similar in formula. You can actually see it, like
Mhm.
if I can get them to match up. But you can see they are very similar in their formula. Permutations has a specified order. Order matters. You're choosing
Matter.
this, then you're choosing this, then you're choosing that. So you're choosing
Mm.
1, 2, and 3.
Mm.
With combinations, order does not matter, which is why there's another R on the bottom. Order
Mm.
does not matter. You can choose it in any order. But permutations, you're choosing it in a specified order.
Permutation specified
In both of these, repetition
order.
is not allowed. So permutations is an ordered
Order.
arrangement. Order is important.
Order.
Objects are chosen from the n number of distinct
Distinct.
objects, whereas combinations
And
is a collection without regard for order. It
order
is not important,
important.
and the objects are still chosen from n distinct objects. So that is the main difference between the two of them. Is order important? Are you choosing in a specific order? If no, combinations. If yes, permutations.
Okay.
And then I think we are out of time for the workshop. But if you need any more help on the stats stuff, I do have some appointments tomorrow, and I think let's see who else does stats during the week.
Gina and Ava do.
Yeah, I know they're mostly online as well.
Mhm.
Um,
Well, Ava is only online. Gina is only in person.
oh yeah, okay.
Yeah.
And then there's also Jesse. He's Thursdays and Fridays, online, and I think Mondays in person.
Mhm.
Um, and then Ava, yeah.
Okay.
All good options for statistics. But yeah, these formulas, they're not tricky to handle. It's all about the wording.
Okay.
Anything else? Any other questions before we end the workshop?
No, no questions.
All right. Well, have a good rest of your day,
All right, you
and thank
too.
you so much for coming in.
No problem. Thanks, Corey. See ya.
See ya.